the last thing that we did was Rushi's theorem. So what does it say? It says that if I have a Jordan curve and in a closed curve domain, then for example, if I take two holomorphic functions and such that mod of f of z is bigger than mod of g of z, then we will have that with the property, yeah, mod of f of z is bigger than mod of g of z, then the number of zeros of f plus g same as number of zeros of f inside gamma. Okay, so that was Rushi's theorem. So gamma was so to start with, D was a closed curve domain and gamma was Jordan curve. And I had Jordan curve on D. And I had two functions f and g which are holomorphic on D, such that mod of f of z is bigger than mod of g of z for all z in gamma. So on gamma, this inequality we have, then we got that number of zeros of f plus z is number of zeros of f inside gamma, or like in the area G. Okay, so this is what we have, and now we can have a similar phenomena over here. Of course, I also said that the zeros like do not lie on gamma, because but that is already ensured by this condition. Okay, so here what I now have is that I can also have an extended version of Cauchy's theorem. Okay, because you can see that our argument principle allows you to also get hold of number of poles together with number of zeros. Okay, so we can also have this extended Cauchy's theorem, which is applicable for meromorphic functions. Okay, so let's say I have exactly the same setup. Gamma is a Jordan curve, and in place of holomorphic function, let us say I have meromorphic function. Meromorphic function on D, and with the same hypothesis. Okay, so mod of f of z is bigger than mod of g of z for all z in gamma. So of course this condition ensures that f is non-vanishing, but at the same time we are saying that this fz gz they take actually legitimate complex number on gamma. So therefore I am also saying that on gamma there are no poles. Exactly on the path gamma there are no poles. So then what I can say is a similar statement: z of f plus g minus p of f plus g would be equal to z of f minus p of f in the area enclosed by gamma, where this the area. Okay, so where I should write this, where this zf plus g pf plus g zf pf denote the zeros and poles of f plus g and f respectively in the area enclosed by gamma. Okay. So this is what we get as the extended version of Cauchy's theorem. So I am not proving this because the proof is essentially identical. Okay, there is nothing that you need to do. So if you remember, in the proof of Cauchy's theorem, we had this three integrals. One was integral over gamma f plus g prime divided by f plus g, which was equal to integral f prime over f over gamma plus integral 1 plus g upon f prime divided by 1 plus g upon f over gamma. And what we realized is that the first integral is going to give me z of f plus g minus z of p plus g. The second integral is going to give you z of f minus z of p of f. And then the third integral, we had to show that the third integral was equal to 0. Exactly what we did in the proof of Cauchy's theorem. There is absolutely no change in place that like when you encounter these two integrals. So this becomes z of f plus g minus p of f plus g. This is by argument principle, and similarly f prime upon it becomes z of f minus p. So you just have these, you just have these two things in addition, and as before, this 1 plus g upon f prime divided by 1 plus g upon f, this guy is still going to be 0 because this is going to be still winding number of some paths. Okay. So the same argument works, and this becomes 0. So absolutely no change in the proof, okay, except for these two. So is this clear to all of you? Yeah, is this clear?
Yes, sir. Yes, sir.
Okay, fine. So now I want to state one more important consequence of this postulation theorem. So let me first can any one of you recall the Cauchy integral formula that we had, and then what was the generalized version of the Cauchy integral formula? Yes, can anybody recall? Come on, you have forgotten Cauchy integral formula.
Integral fz by z minus a to the power n plus 1 is equals to 1 by 2 pi I into f of a.
Not quite f of a, but okay. So it is you are close, but also needs to be slightly careful. So we had seen that the kth derivative of f at a is given by k factorial divided by 2 pi I a plus gamma rho f of z divided by z minus a power k plus 1. This was the formula, right? Indeed, this was the formula.
Yes, sir.
Okay. So this was the generalized Cauchy integral formula that I had written. Of course, here you can recall that the Cauchy integral formula, of course, I can write it for f of a, k fact, sorry, there is no k factorial, 1 upon 2 pi I, a plus gamma rho, f of z by z minus a. Of course, that's Cauchy integral formula for a. But in fact, in general, Cauchy integral formula, I can write I do not need to take, you see, here the center is A, and also the circle that I am taking. So the gamma that I have over here, that's a circle of radius rho centered at A. Okay, so that is not really required. I can have actually f of alpha to be A plus gamma rho f of z by z minus alpha. I can have that. Okay? But nevertheless, the way we got this generalized Cauchy integral formula, we could only get the kth derivative at a. Okay, so where the curve was taken to be a plus gamma rho, and here I have z minus a. So I could only do it for particular for the center. Here at least alpha is not the center. My circle is centered at A, whereas alpha is something. Of course, you need to have this mod of A minus alpha is less than rho, and it is holomorphic in some ball containing all this. Okay, so that's the picture. But now that we know the Cauchy-Descriptive theorem, we can state this Cauchy generalized Cauchy integral formula in the in a more general sense. Okay, so let me tell you what is the statement that I can get. So generalized Cauchy integral formula. Okay, so you remember now that whenever you have a closed curve domain and just a Jordan curve, immediately you are going to be able to write down this Cauchy integral formula or generalized Cauchy integral formula for any point that you wish to write this kind of integral for. Okay, so let f let D be a closed curve domain. Let D be a closed curve domain, and f belongs to H of D, and gamma be a Jordan curve on D. Okay. Then for any alpha belonging to the area enclosed by gamma and k bigger than or equal to 0, we have f k derivative at alpha is equal to k factorial divided by 2 pi I integral over gamma f of z divided by z minus alpha power k plus 1. Okay, so this is what we are going to get. Okay? So that means now, of course, I was telling you in all other this Cauchy integral, whether it was Cauchy integral formula or generalized Cauchy integral formula. For instance, I was telling you that the paths that we were taking at that time, they were all circular paths. Number one, and moreover, for the generalized Cauchy integral formula, what we did is that we in fact said that the kth derivative, we could only express the kth derivative at the center by using an integral formula where the integral is over a path, over a circular path. But this time I am not saying that. This is a very general form. It just says that you have any closed curve domain, and on that you take whichever type of path you like. It need not be circular. All you need is it should be a Jordan curve, and then of course even if it is a circular path, you can think of a center, but you really do not need to take any center for that sake. You can take any point alpha, and then what it says, that the kth derivative of f at alpha is going to given by this integral. Okay, so this one is a much more general form of this generalized Cauchy integral formula. All of you see that? Yeah, previously, if you remember, I only had fk at a was k factorial divided by 2 pi I, a plus gamma rho, f of z divided by z minus a power k plus 1. I only had this one previously. Right, so clearly this is a circular path. You have a over here where a is the center of this circle. But this time I just have nothing. of course my integrand remains the same, which is natural, but my curve could be anything. It could be any Jordan curve, and my alpha could be any point which is lying in the area enclosed by this curve gamma. So are you able to see the difference now clearly?
Yes, sir.
Yeah. So here that's why now we have the generalized Cauchy integral formula in the most general form that one can expect. Okay. So let us see if we can prove this. The proof should be immediate, in fact, okay, because the proof is very simple. It's in fact just an easy application of Cauchy residue theorem. So we will see that. Let's do it. Okay, fine. So now, of course, I have a point alpha and I have a holomorphic function on D, and I want to integrate my function over there. Okay, that's fine. All right. Now, what can I write? I can, so note f of z. So, you see, I want to talk about, so of course I need to show that this integral over here, whatever I have, that integral should be the kth derivative of f at alpha. Okay. So therefore I need to calculate this integral. Now gamma is a closed curve, f is a holomorphic function. I have a factor dividing f, which is z minus alpha power k plus 1. So therefore this integrand over here that I have, that's a meromorphic function. So that's fine. And so therefore I want to figure out what is this what this integral is. So I will apply Cauchy residue theorem. Now if I want to apply Cauchy residue theorem, tell me, look at the integrand, which point do you think is a singularity for this particular function? What is that point?
Alpha.
Alpha is the singularity, right? So therefore, what I have to do to integrate this function by using Cauchy residue theorem, what information do I need? Tell me. What is the information that I will require to use Cauchy residue theorem? Yeah? Tell me, what information do I need?
Alpha is the pole of order.
Sorry, Abhishek, I can't hear you.
What is the order of pole?
Yeah, that's the order, is the order of pole. And once we understand what is the order of pole, then what else do I need to use Cauchy residue theorem?
Residue of this function at alpha.
Residue of this function at alpha. Okay, great. So now how do I find residue? Residue is found, of course, like there are formulas which are given to us. We can of course use that. But otherwise, residue is also found, like you can also find it by, for example, looking at the Lorentz expansion, right? So here, in particular, of course, you can use the formula that I have given you. But here I can also tell you that the using the Lorentz expansion is also not quite difficult. So how do I get a Lorentz expansion? First of all, I know that f is a holomorphic function at alpha. So therefore, what I will be able to do is that I will be able to write down my function in a neighborhood around alpha. Okay, so what will be the expression of the power series? This will be f of alpha plus f prime alpha into z minus alpha plus f double prime alpha divided by 2 factorial z minus alpha square, so on so forth. I will have f kth derivative at alpha divided by k factorial z minus alpha power k and plus so on so forth again. Do you agree that this is how the power series expansion of f around alpha will look like, right? All of
Yes,
you
sir.
agree, right?
Yes, sir.
Now,
Yes.
from this expression, can you quickly tell me what is the residue of f of z divided by z minus alpha power k plus 1 at alpha? Can you tell me what is this residue? Just look at this expression and put it quickly.
F get derivative alpha upon the k factorial.
Absolutely. So, if k derivative of alpha divided by k factorial. How did you get that?
1 upon z minus alpha का coefficient.
Exactly. So we know that by definition, residue is the coefficient of 1 upon z minus alpha. So once we write down this power series expansion, I immediately get this one. Okay, so of course you can use the formula which I have given you to figure out the residue. You will be able to do it in the same spirit. Okay, anyway, so I get that this is my residue. So therefore, hence, by Cauchy residue theorem, again this is not Chinese remainder theorem. Cauchy residue theorem 1 upon 2 pi I integral over gamma f of z divided by z minus alpha power k plus 1 is what? Of course, here I can write this integral is equal to, forget this. So this integral is equal to 2 pi I times, what's the integral? 2 pi I times
Binding number of alpha and residue of
winding.
at alpha.
But here I am taking a Jordan curve. So what will be the winding number? And alpha
Binding
is
number will be 1.
1 because alpha is belonging to the area enclosed by gamma. So therefore the winding number is 1 and the residue is the kth derivative at alpha divided by k factorial. So are there any other singularities of this function or alpha is the
No,
only?
sir.
So alpha is
Alpha is 1.
so therefore this is kth derivative of alpha divided by k. So this is the proof, right? This is precisely I wanted to prove. Of course, I have k factorial and 1 upon 2 pi I in the other side. That's just a trivial. Fine, is this clear to everybody? Yeah?
Yes, sir.
Okay, so now you see that we have a very general or like the most general form of this generalized Cauchy integral formula, where neither our point of interest needs to be the center of a circular path, nor the path itself has to be a circular one. Okay, great. So now that's one application which we see that the Cauchy integral formula we can have a more general version of it. Fine. So next comes another theorem which is about the convergence of holomorphic function. Okay, so let me see. Uh, let me tell you the statement first. Theorem. So let Fn be a sequence of holomorphic functions on D such that Fn converges to F uniformly on every compact subset of D. Okay, so I have this much. So then what can you say about F? Anybody can tell me? What can I say about F?
F will be continuous.
F will be continuous, a little bit more than continuous, anything else?
Holomorphic on D.
Yeah, very good. Then actually this we saw as an application of Morera's theorem. Then because F is holomorphic on D, this is I am not much more interested in. This we have already seen. F is holomorphic on D. Moreover, Fn prime converges. So all these are holomorphic, so I can take derivative. Converges to F prime uniformly on compact subsets. Okay, so what it says is that I need to have this uniform means I whenever I have a sequence of holomorphic function and sequence converges uniformly on compact subset, then the function image function itself is holomorphic, and the derivative of the sequence also converges to the derivative of the function, and that convergence is also uniform. So this is precisely what I would like to show, and of course for the proof, holomorphicity of F follows from Murada's theorem. So I'm more interested about the uniform convergence of the derivative. So how do I prove this? I need to prove that I have uniform convergence on all complex subsets. So what I'm going to do, I'm going to prove uniform convergence on disks. Okay? And then if I take any complex set, I can cover them by finitely many disks. So therefore, we will be done. Okay? So effectively, I need to work with disk. So we show uniform convergence of f prime or fn prime on let's say closed disk here. Okay, doesn't matter. So if I have uniform convergence on closed disk, then I will also have uniform convergence on open disk as well. Okay. Fine. So let us take a disk. Let some b z naught delta bar is subset of D. So I'm taking some disk like this, and then I have to show the uniform convergence on these disks. Okay, fine, that's all right, no issues. Let us write down the functional values, the derivative. Okay, so here remember one thing, that I am dealing with the derivative, and I would like to use the uniform convergence of f, which is already given to me. So therefore, the best thing is to express your derivative in terms of your original function. Okay, and just now we saw a way of expressing derivative in terms of the original function, which was by means of this Cauchy integral formula or generalized Cauchy integral formula. You see here I have derivative, but inside the integral I have the actual function. Okay. So we are going to use that. So let's see how can we do that. So right. So for z in, let's say, bz not delta bar, or let's say for alpha, right, f n prime at alpha, this is 1 upon 2 pi I integral, let's say here I can take z naught plus gamma delta f n w divided by, so f n z divided by z minus alpha square. So that's the formula. And similarly I have f prime at alpha is 1 upon 2 pi I integral z naught plus gamma delta, just a second. Okay, so z naught plus gamma delta f z divided by z minus alpha square. Okay, I just write the same expression for fn prime and f prime. Okay, so therefore what's the difference between these two quantities? So fn prime of alpha minus f prime of alpha, this is 1 upon 2 pi I integral over z naught plus gamma delta. So this means circle of radius delta centered at z naught. So fn z minus f of z divided by z minus alpha square. This is precisely what I have. Okay, fine, all good. Now what I am going to do is that here notice one thing. I am going to have uniform, means I already have uniform convergence of my function. Okay, so all these z and alpha, all of them are sorry, yeah, this alpha is inside this ball. Okay, so I'll rather take alpha inside this ball. I'll take alpha from this ball, and my z is varying over this circle. Okay, so what happens? Of course, everything is fine. Like the denominator is also non-vanishing, no problem on gamma. But I have uniform convergence. So what I can do? So by uniform convergence of Fn to F, we can choose, let me write, for a given epsilon positive, we can choose n naught such that mod of Fnw minus Fw is less than epsilon times delta for all n bigger than or equal to n naught. Okay, in fact, this I can do it for all the points over there. Sorry, this is z, fn z minus f of z for all z. Okay, this is precisely what I do. Okay, all good. This is the estimate that I get. Now, if I use ML inequality, I get Fn prime of alpha minus F prime of alpha. This by ML inequality, I have 2 pi over here. Length of the integral is, length of the path is 2 pi delta, because it's a circle of radius delta. The numerator is bounded above by epsilon times delta, and the denominator, if you see, the denominator is,
delta square.
yeah, definitely uh, bigger than delta square. So therefore, what I have is that this is less than 1 upon delta square. So what I get is that, just a second, did I do it correctly? Here you can see that mod of z minus alpha. No, I think I have made a mistake over here. Just a second. So this one, alpha is inside the ball. I take any point from those points. It is no, no. Here I have done some mistake. It looks like, just a second. So let's see. Yeah, here I need to be slightly more careful. Yeah, so I need to work with uh, here I think a ball yeah, of delta by 2. Yeah, so I will show uniform convergence on these kind of balls of radius delta by 2, like that way. So here I therefore have this distance. So alpha is inside ball of delta by 2, and my points are on the circle of radius delta. So this so mod of z minus alpha is bigger than or equal to delta by 2, and therefore when I take reciprocal, so I get 4 times this. So I can take a 4 over here. So therefore this will cancel, and I will do the square root. So this is equal to epsilon. Okay. So what I am doing here is that I am taking any point, means like that I am taking any delta ball. So you can choose uh, these kind of balls. For example, you can think of showing uh, uniform convergence, let's say, on any kind of ball which is of radius less than half or something, and then you choose some ball which is inside this domain, and you write down the integral expression over there for such kind of balls, and then if you take any z, any alpha from here, you see that the difference between fn prime of alpha and f prime of alpha, that's uniformly less than epsilon for any alpha. So for all alpha, for all alpha in b z naught delta by 2. Okay, so no matter what kind of like I can always for any compact set I can pack them by small, like whatever open cover I would like to take, I can then pack. I can find a neighborhood consisting of this kind of or open cover consisting of these kind of neighborhoods, and where I have this uniform convergence, and I will get a finitely many cover. So therefore, we will get uniform convergence on compact subset. Okay, so this by taking any open cover of a compact set, and then by open balls, and then by taking finite subcover, we will get uniform convergence on compact subsets. Okay, so this is what we can see is that not only Fn converges to, means when Fn converges to F uniformly, sequence of holomorphic function, of course the limit is holomorphic, but we also have that the sequence of the derivative that also converges uniformly to the sequence of derivatives. Okay, fine. So we will continue looking at some of the sequences of holomorphic functions in the similar spirit. And next thing which we will prove is a theorem due to Hurwitz. So what is theorem of Hurwitz? So here, these ones are quite powerful. This one is going to tell you that if you consider non-vanishing holomorphic function, and if you try to, find uniform limit of those things, then your means up to some special cases, your function limit function will also be non-vanishing. Okay, so let us see what is the statement of Hurwitz. So let Fn be a sequence of non-vanishing holomorphic function on a domain D on a domain D. Let Fn converge to suppose Fn converges to F uniformly on compact subsets of D, then either you are going to get F is identically 0 or F is non-vanishing on D. So that means either you will get identically 0 function or it will non-vanish. So if it is non-zero at one point, you will know that the limit function is going to be non-zero everywhere else. So this one, of course, I cannot rule out the possibility of f being identically 0, because for example I can take fn, let's say, to be just 1 over n, constant function 1 over n. You can even take non-constant functions, but suppose I take fn to be constant function 1 over n, then this sequence is a sequence of non-vanishing holomorphic functions. It's going to converge uniformly on compact subsets, but then the limit function is not is identically 0. So the limit function is not non-vanishing. So therefore we cannot rule out this option, that has to be there, and we will see the other one. So if f is identically 0, we have nothing to do. So let f is not identically 0. So if f is not identically 0, then what do I have to show? I have to show that then f even does not vanish anywhere. So we need to show f does not vanish on D. So if it's non-zero, that means it will never vanish at any point. This is what we need to show. Okay, fine. All right. So suppose f has a point, like f has a 0. So suppose f has a 0, say at z naught. Say at z naught. Suppose f has a 0 at z naught. Now since f is not identically 0, by identity theorem, what I can do is that I can find out a circle where f does not vanish on the circle. Since f is not identically 0, by identity theorem, we can find some circle or some closed path, Jordan path is fine. We can find a circle z naught plus gamma delta where f does not vanish on this circle. Okay. Now remember one thing. I have that my function is not vanishing on this circle, and of course my function fn, they anyway do not vanish. Okay. So if I consider this sequence of function fn, this I know this converges to f uniformly on compact subsets. Fn prime, they will also converge to f prime uniformly on compact subsets. This we just proved. And since Fn do not vanish and F also is not vanishing on the circle, so we have Fn prime divided by Fn converging to F prime divided by F uniformly on at least Z naught minus gamma delta. Because I know that Fn is anyway non-vanishing, that is given, but F is also non-vanishing on Z naught plus gamma delta. So I have this uniform convergence on this side. And once I have this uniform convergence, we know what we can interchange integral and limit. Okay, so what is the integral? So here 1 upon 2 pi I integral of Fn prime over Fn converges to 1 upon 2 pi I integral. So this is Z naught plus gamma delta, Z naught plus gamma delta, F prime upon F. Okay. Now, what is this integral? Can you tell me what is this integral? What do we? This is. Tell me, this is what?
Number
No, by you have seen already argument principle, right? So what is this? F is a holomorphic function, so therefore this is Z of Fn, right? Correct?
Yes,
Z
sir.
of
Yes,
Fn,
sir.
right? And I'm counting only the zeros inside this circle Z naught plus gamma delta. So what is that number? Can you tell me? Z of Fn
0.
is 0.
0.
And what is this quantity? Again?
Again 0 F and this will again 0.
No, this is not 0. This is what I have assumed. I have assumed that f of z naught is equal to 0.
And this one is 1.
So this guy is
1.
bigger than or
1.
equal to 1. But I am getting that the sequence of 0 should converge to a sequence to converge to a limit which is bigger than or equal to 1. So this is a contradiction, right?
Yes, sir.
Contradiction. So why did I get this contradiction? Because I got this contradiction because I assumed that even if f is non-vanishing, I could find a 0 of that particular. Even if f is not identically 0, I can find a 0 of the function z naught. So that means this assumption is not true. So hence f is non-vanishing. So these are very powerful results, as you can see. So it says if you take a non-vanishing function here and a sequence which is converging uniformly to another holomorphic function, that image is also going to be non-vanishing. So this is what is theorem of Hurwitz. Okay, and this has a very nice and simple corollary. Here, of course, I was talking in terms of you know vanishing or non-vanishing. So the corollary is in terms of a function being injective or not. So let me write down the corollary. You will immediately see how it can be put. So let Fn be a sequence of holomorphic functions on a domain D. Let Fn converges to F uniformly on same hypothesis compact subsets of D if Fn's are injective, that means 1 1 function, then either F is constant or F is injective. Okay, so I can have a scenario where, like for example, if I take let's say Fn equal to z by n. Okay, so then this is a injective sequence, and on every compact subset, this is going to converge to 0. So the limit function could be constant; it need not be injective. But if it's non-constant, then it will be injective. That's the statement. So if I start with an injective sequence, the limit, the uniform limit of a sequence of holomorphic and injective function is always going to be injective unless the limit is constant. Okay. So again, I can give the proof is very simple. If f is constant, we have nothing to prove. And so let f be non-constant. So suppose f of z1 is equal to f of z2 for z not equal to z1 not equal to z2. Suppose I have this scenario. Now what do I have to show? I have to show that my function is I'm supposed to show function is injective. So I'm assuming I'm going to prove it by contradiction, and I'm assuming 2 points z1 z2 which are not equal. Then and then f of z1 is equal to f of z2. This is what I am assuming. Okay. Fine, all good. Now notice note, if I consider this function gn of z, which I define by fn of z minus fn at let's say z1. Yeah, I define gn to be this one, fn at z minus fn at z1. Okay. And okay, so rather let me do it in this way. Yeah, this is fine. This. So I take gn to be this, and then since fn is injective, we get that on d minus z1. So I am just removing one point from my open connected set. It's still going to remain connected, open connected everything. There will not be any problem. So then since fn is injective, we get that on d minus z1, gn's do not vanish. All of you agree to that?
Yes, sir.
Okay, fine. So now these gn's are non-vanishing because here I will never get fn of z1. The same value I will never get. So therefore, this will not cancel. So gn's do not vanish. Now, what about the convergence of gn? Because convergence of fn is uniform. So therefore, what we get is that now gn's converge. Tell me, where does it converge to? Yeah, what is the limit function? G of z, let's say. What will be the definite, what will be the limit function g of z?
fz minus f of z1.
Fz minus f of z1. Very good. So now gn's converge to gz over here. Okay. Now what can I say about this g function? Does it vanish anywhere?
No, sir.
No. Look at the hypothesis and then tell me. Does it vanish anywhere on d minus z1?
Yes, sir, at Z1.
At z2, not z1 not. There is z2 here. Yes, but g of z2 is equal to 0 as f of z1 is equal to f of z2. Okay, now I have a sequence. Here I should write uniformly. on complex subsets. So here I have a sequence of non-vanishing function which is converging uniformly, and the limit is vanishing at a point. So this implies what? By Hurwitz's theorem,
G is identically 0.
G is identically 0. But if G is identically 0, that means what?
F is constant.
F is constant. Very good. But we started assuming that F is non-constant, so we get a contradiction. So sorry. Sorry.
How do we get GNs do not vanish? Because if we put GN Z1, then it will 0.
Yeah, but my domain is D minus Z1, right? I have removed that point.
Okay, sir.
If you remove one point, you are on complex plane, you will still have open connected set. No issues. Right? Clear? So therefore, I get that G is 0 and F is G is 0 implies F is constant, and that gives you a contradiction. So therefore, like we get some interesting properties of convergence of holomorphic, like sequence of holomorphic functions. So whenever we have uniform convergence, we see that the sequence of functions, their limit, like if I have uniform convergence of compact subsets, if I have a holomorphic sequence of holomorphic functions, then the image is going to be holomorphic, the derivatives are going to converge uniformly. So all these things are there, and we moreover, not only that, we get that if we have a sequence of function which is non-vanishing, then either the image, the limit sequence, limit function will be identically 0, or it's going to be non-vanishing. So either it vanishes everywhere or it vanishes nowhere. Okay? So it's between these two extremes we are going to have this case. Similarly, if I have a sequence of injective functions, then image could be constant in the sense nowhere it's like no 2 points the image is different, or for any 2 points the image are going to be different. So again the two extreme, that either at no, like for every, like no 2 points are going to go to the same point, or all the points are going to go to the same point. So that's the nice little properties that we observe as corollaries of this Cauchy-Destrich theorem. So now I come to this doing integration, rather real improper integrals using Cauchy-Destrich theorem. So another segment of application of Cauchy-Destrich theorem. So doing improper integral using Cauchy-Destrich theorem. Okay, great. So let's see. So here I am going to take certain kind of scenarios, and then I'm going to tell you, elaborate the process, tell you the formula. Okay. So if you remember the process, that's good for you. Like in case you forget the formula, you will be able to still recover it. But as far as like for practical purposes, if you remember the formula, that is good enough. Okay. But like often, if you like remembering anything without understanding becomes difficult. Okay. So you can think of that, okay, this segment will, there will be many formulas, and therefore like you will be, once you know the formulas you can apply them uh, to solve like these kind of problems, whether it is in our exam for the course or in general exam for competitive exams and other kind of things. So that's why like in the beginning I told you that complex analysis has many applications, and generally in competitive exams you are asked about these kind of applications, these kind of problems. So this is another segment. Okay, so where we see application. So the first thing, this is the first form of improper integral. So let me write type 1. So type 1. So what's type 1 here? So we want to integrate rational functions. So rational functions means it's ratio of two polynomials, minus infinity to plus infinity, px upon qx dx. Okay. So this is the general form of the integral, but of course I need certain condition to make sense of the integral, and where first of all I put that q of x is not equal to 0. So that means the polynomial in the denominator that does not vanish on R. And number 2, for to ensure that my improper integral converges, I require that degree of q minus degree of p is bigger than or equal to 2. 1 is not sufficient because integral over 1 over x or like that kind of thing, x mod of x plus 1, let's say, those things do not converge. So I have that. So this is degree of qx, q minus p should be at least 2. So this is the integral that we are going to do. So here I have to tell you something about, first of all, the notion of improper integral. So whenever you have improper integral at both the ends, the idea is to you break it somewhere in between, and the individual integrals need to converge. Okay. And of course, since here my hypothesis is such that it will already ensure the convergence, and therefore we can take a different definition, not different definition, but we can use a different formula. Okay. So generally, what is the formula for this, for minus infinity to plus infinity? Px by qx dx. So let's say this should be equal to limit, let's say n1 tends to, or let's say limit n tends to infinity, 0 to n px by, or let me write r, some r, let's say r1, px by qx dx plus 0 to, let's say, minus r2, limit r2 tends to infinity, 0 to r2 minus r2 px upon qx dx. Okay, in place of 0 you can also have a, doesn't matter, any point. So somewhere you break it, and then like, which is where you can do legitimate uh, Riemann integration, and then you can just take the positive you can go to the positive side, and you can show that the integral exists, or you can go to the negative side, you can show the integral exists, and then eventually you add both of them to get the improper integral minus infinity to plus infinity. So this is the definition. Now the point is, here as I have degree of q minus degree of p is bigger than or equal to 2. So this ensures that both these two limits, they do exist. Okay. So once both these two things, they do exist, of course I can write in place of r1 and r2, I can just write since the given conditions ensures that both the limits exist, we can write them as, we can write minus infinity to plus infinity px by qx dx is equal to, here I can just replace r1 by r, 0 to r px by qx dx plus, let me again write r. Of course, when I am writing in terms of two separate limits, this r1 and r2, there this r is still different from one case to another. Px by qx dx. But when you know that limit of two things exist and you sum them, that becomes limit of the sum. So this is, I can write limit r tends to infinity minus r2 plus r dx upon qx dx. Okay, so of course existence of these limits are guaranteed, and therefore I can write like this. Okay, so remember one thing, that this formula is not the definition. This is not the definition. This comes out due to the conditions that I am imposing. Okay, so that's not the definition. Definition is this one. The improper integral definition is this one. But since here the conditions ensure that I am going to get convergence, so I can write like this. Right. So this is the formula I am going to work with. Okay, great. So I have to integrate from minus r to r px upon qx dx, and whatever limit comes out to be, I need to take the limit for like integrate and then take limit r tends to infinity. Fine. So how do I do this? I'm going to do this using some contour integration. So what's my contour? Let me try to draw this. I'm not good at drawing, but I'll try. So let's say this is my coordinate system. I will change the color. Okay, so what's my contour? My contour over here is this one. So this is minus r2 plus r. I have this straight line toward the real line, and then I have this half circular contour. This one is I times r, this point, this half circular contour. So this is the contour that I am taking, or the closed curve that I am taking. These are piecewise smooth and all that. Everything is clear, and I'm going to integrate my function on this contour. Okay, so let me write down. So I'm calling it gamma r. So let gamma r denote the contour consisting of number one, the line segment from minus r to r, and number two, the semicircle of radius r in the upper half plane. So this is precisely what I have. Okay. So now, of course, I need to, you see, integrate, remember, px upon qx from minus r to plus r. So, of course, for the integral, for this contour also, on this contour also, I am going to integrate the same function. Okay. So, we see that integral over gamma r, my function here is pz upon qz. This is nothing but integral from minus r to plus r dx upon qx dx plus integral on this semicircle pz upon qz. So I have this. Okay, And now remember, I need to calculate this integral, and then I have to take r tending to plus infinity. And I will get this integral provided I know this one as well as this one. Remember, my target quantity is this one, so I have to take care of this guy and this guy. Okay. So now, if we understand what we really need, one thing should be very clear. This gamma r, this is a like a Jordan curve, piecewise smooth and all that. Everything is fine. So here, when I integrate Pz upon Qz, what I am going to get is the, by Cauchy residue theorem, it's going to be 2 pi I times sum of the residues. Okay. So this integral, note, by Cauchy residue theorem, integral over gamma r Pz upon Qz is equal to 2 pi r summation residue of P by Q at the point zk, where zk's are the singularity of P by Q inside gamma r. All of you agree to this?
Yes, sir.
Okay, so this is going to give me the singularities on this. Okay, so anyway, I have said Q does not vanish on R, so there are no singular points on the real line, but it could have, Q will have zeros. Anyway, it's a polynomial, so it will have zeros somewhere in the complex plane. So I'm saying this integral over gamma r is going to be 2 pi I residue P by Q z. That's what it is. Now, here, of course, you remember at the end, I need to take limit r tends to infinity. Okay. So, if I take, hence, once I get this, tell me what is this limit r tends to infinity integral over gamma r pz by qz? What is this quantity going to be? This is going to be what? Imagine I increase my r, I take bigger and bigger r. So, that will encompass all the singularities of P by Q in the upper half plane, right?
Yes.
Isn't it? The more I increase my R, I am going to encompass more and more number of zeros or of Q, or let's say singularities of P by Q, which are lying on the upper half plane, correct? So therefore, is it clear to all of you or not?
Yes, sir.
So therefore, I can write this limit is 2 pi I summation residue of P by Q at the point zk, where zk's are singularity, which is same as zeros of Q, singularities of P by Q, unless P and Q have a factor in the upper half plane. Fine, all of us agree to that?
Yes, sir.
Yes.
Okay, great. Now I need to take care of this integral on the semicircle. Okay, so let's look at this integral on the semicircle. So note, here you see I am given that the polynomial q is having degree at least 2 more than the degree of p. So when I imagine this function as p by q, okay, so this function, so like I have already told you this, if you take a degree n polynomial with some with some coefficient, let's say, or let's take a monic degree n polynomial, monic means coefficient being 1, then the growth of the polynomial, that particular polynomial, is actually of the form z power n. Okay, if I am taking a monic polynomial of degree n, then the growth of that polynomial, like in absolute value, is about mod z power n. Okay. So similarly, like if you have some let's say your leading coefficient is some constant c, then the growth of the polynomial will be some constant times mod z to the power n. Okay, so that I have already explained to you. So here, of course, eventually you understand that I am going to take r tending to infinity. That is going to be there. Now, if I take r very large, okay, then what you can see is that here I have the numerator p, sorry, not here. Here, the numerator is p, which is, let's say, growing like r power n, and q is a polynomial which is having degree at least 2 more than the degree of p. So then the denominator is going to grow like mod z to the power n plus 2. So in comparison, the ratio is going to grow like mod z to the 1 upon mod z square at least. Is this clear to you what I am saying?
Yes, sir.
I am interested about the growth of this function on this semicircle. So here what I am trying to say is that, of course, like since I do not have explicit estimate and all that, I'm going to use ML inequality, which is evident. So for ML inequality, what I need a bound for this Pz by Qz and the length of the semicircle. And the length of the semicircle is trivial, that's pi times r. And this Pz upon Qz, I need to understand what is this. Both P and Q, they're polynomials, and degree of Q is at least 2 more than the degree of P. Okay. So we know that mod of Pz is about mod z power degree P as mod z tends to infinity. Similarly, mod of Qz is about mod z to the power degree Q. Sorry, sir, there will be some constant. So let me write some CD. Degree PQ as mod z tends to infinity. So totally, so for large R, we have mod of Pz by Qz is roughly about some constant again. Let's say I write some C prime mod z to the power degree P minus degree Q. Okay. And this is degree P minus degree Q. You know, it's Q is degree Q minus degree P. I know is bigger than or equal to 2. So therefore, this quantity will be less than or equal to some C prime mod z square. Yeah, all of you agree to that?
Yes, sir.
So let me, so as mod z tends to infinity. Okay, so hence, so for large enough n or large enough r, we get the integral on semicircle Pz upon Qz in absolute value is less than or equal to what is the length? Length is pi r into some C prime divided by mod z is on r on this circular arc, your mod z is equal to r. So I get r square, so which is equal to pi C prime divided by r. And this goes to 0. This tends to infinity. All of you agree to this? Yeah.
Yes, sir.
So hence, you see, now at the end, as I said, I am supposed to take limit as r tends to infinity. You know what is this limit as r tends to infinity, and you know what is this limit as r tends to infinity. So that gives me what? Finally, tell me what do I get? Integral minus infinity to plus infinity. Px upon qx dx is equal to what? Look at the formula what we have and tell me what should I get. Is equal to, tell me, Sorry, cannot hear you.
2 pi I into summation of residues of P by Q in upper half plane.
It is effectively this. There's nothing else. Okay, so now if somebody gives you an integral of this form, you will actually, of course, if you can remember this formula good, otherwise also like you can take this kind of contour, use some kind of argument. You will see in most cases on the circular arcs, we will always have some suitable way of bounding our function. Okay, and on the straight lines and those kind of places where we really have to, means those integrals are going to give us the integral that we desire. Okay, so you will take contours accordingly. So this is what is the formula that we get finally. So let's write down. Let's see an example. Okay.
So ये infinite sum नहीं है.
Yeah, this could be infinite sum, no issues. But if it is, see, if the sum is infinite, you are not going to get, like, whether it means here your q, like it might look like that, but your q is a polynomial. So how many zeros will it have? Finitely many zeros. So p upon q is going to have only finitely many poles, right?
Yes.
Right. Eventually, after some time, this limit is not going to change. Like, you can, of course, when you take initially some r, your gamma r might not contain all the singularities of p by q. That might be true, but effectively when you take large enough r, you will be able to encompass all of them, right? So after some time, anyway, there will not be any change in that sum. And also, as I said,
And so those singularity which are below, मतलब lower half circle or what?
yeah, so they are not appearing over here. You need to only, because the formula tells you only need to look at the upper side. So of course you could have drawn a similar, you know, a similar contour going through the lower half plane. Then you would have taken the residue of the zeros at the lower half plane. That would have given you the same integral, because there is no difference here. I have taken one integral of my choice. Of course, you need to be careful once, because when you take uh, semicircle on the lower half plane, then you see that your path becomes clockwise. So your integral should come with a negative sign, okay, because your winding number will be -1 in that case. Okay, so here taking the main reason of taking the semicircle on the upper half plane is so that your curve, the orientation of the curve remains in the positive direction. Fine. Otherwise, there is absolutely no difference. You can take the semicircle on the lower half plane as well, and but only thing you need to be careful. Then you will encounter, like, you need to count those singularities which are there on the lower half plane. But remember, then you have to remember that you need to adjust the sign. Fine. Is it clear, Abhishek?
Yes, sir.
Okay, so that's all. So let's see an example. So I want to figure out what is minus infinity to infinity dx upon x power 4 plus 1. Okay, so this is what I want to calculate. So since this is the last thing I will do today, calculate this one. Okay, fine. So here, of course, singularities of 1 upon z power 4 plus 1 are those complex numbers such that z power 4 is minus 1. So if z power 4 is minus 1, that means z power 8 is 1, but z power 4 is not equal to 1. And so therefore, what are those ones for which z power 8 is 1, but z power 4 is not 1? So these are e to the power 2 pi I by 8.
At the root infinity.
Yeah, 8th root of unity, but I need to, yeah, exactly. The primitive, let's say primitive 8th root of unities. Okay. 4th root of unities are going to be not there. 2 pi I 5/8 to the power 2 pi I 7/8. So these are the 4 points. Okay. Now out of these, I think only 2 of them are in the upper half plane, because here the angle is pi by e power I theta, so theta is pi by 4. Here it's pi by 3 pi by 4, but here is 5 pi by 4, and here it's 7 pi by 4. So these 2 are in the lower half plane. So out of these, poles on the upper half plane are half plane are e to the power 2 pi I by 8 and e to the power 2 pi I 3 by 8. So these are the 2 points. Okay, so I need to figure out what's the residue. So residue of 1 upon z power 4 plus 1 at e to the power 2 pi I by 8. Okay, now this one is a pole of order. Which order? Tell me, what's the order of the pole here?
1.
Simple. So this is already in the form of a by b. Okay, so I told you that the residue is going to be therefore a at z naught divided by b prime at z naught. Okay, so now the derivative is 1 upon 4 z cube. So this is 4 z naught cubed. So what is your z naught? Z naught power 4 is minus 1. So if I multiply by z naught, so this is z naught divided by minus 4. So where z naught is e to the power 2 pi I by 8. So that's the first residue. And the second, so this is, you can calculate what it is coming out to be. And similarly, the residue of 1 upon z power 4 plus 1 e to the power 2 pi I by 8. This guy is going to be again z naught by 4 minus 4, where this time z naught is e to the power 2 pi I 3 by 8. The same thing. So you just need to put these things and calculate. So in the first case, the residue, so z naught by minus 4 becomes, I think, minus 1 over 4. This one is e to the power 2 pi I 8, so that's cos pi by 4 plus I sin pi by 4. So this is 1 by root 2 plus I 1 by root 2. That's the first case. And so let me write it. This is z1. Let's say. So z1 by 4 minus 4 is minus 1 over 4. So what is cos 3 pi by 4? Cos 3 pi by 4 is minus 1 by root 2, I think. Minus 1 by root 2 plus, and sine is still the same. And therefore, what do I have? The integral minus infinity to plus infinity dx upon 1 plus x square, sorry, 1 plus x power 4 is what? I need to take 2 pi I times sum of the residues where the singularities are on the upper half plane. So I have 2 pi I already multiplied, and then I need to sum the residues. If I sum the residues, these two terms are going to get cancelled. So I get minus 1 over 4 times 2i by root 2, if I am not mistaken. So here 4 gets cancelled, and I square is minus 1, so I get pi by root 2. Okay, check if I have done it correctly or not, but I seem to be getting pi by square root 2. Okay. So this is one type of integral that I have done. Because I'll do some more types of integrals, and we will see how, depending on various scenarios, you can use contour integration to calculate this improper integral. In fact, later we will also do some evaluation of infinite series as well. Okay, we will see all those uh, in the next class. But anyway, Thursday is quiz, so next week. But if I need one extra class which I am losing for the quiz, I will ask you at that time. Okay. So I'll stop here for today. Tell me if there are any questions.